So to generate such a hash function, in this page you are now to use a new technique. It's called MinHashing. So this MinHash can generate a signature for each document based on the signaling results actually. So in this MinHash function, this method, we assume this row of this matrix, the matrix we showed before, this boolean matrix we showed before, we permutated, randomly in the rows. We assume so. And we define this hash function for the MinHashing as a function h. Its own sum of the document, the sets. It denotes the number of the first row in which the column C has 1. So given a document is a set, right? Given it's a set, and we define hash function on this set, on this column, denoting the number of the first row, or the first k row in which the column C has 1s. So this first, denoting in the order of the permutation order actually. This permutation order will be, randomly generated. We'll show this with some examples in the following pages. So because this permutation order is randomly generated, it can be very different in different times, right? So therefore, to make this hash function more reliable and stable, we will use several independent hash functions at the same time to create a signature for the documents. In other words, we will use many of such hash functions because this one is generated randomly. So with more of this hash function, we can achieve a very reliable and stable or converged signatures for the documents. And we will have an observation for supervising properties for such MinHash function, and the probability of all the permutations of the rows that the hash signature of document C1 is the same as the signature of document C2 is the same actually as the similarity between these two documents. So how does this MinHash function really works? We will show you with some examples. So in this page, we'll show you with a concrete example, right? And let's assume we have the input matrix. This matrix denoting the boolean matrix we showed before. Here we only have 2 documents. However, here we have 4 different documents. This is the first document, this is the second one, this is the third one, this is the last column denoting the 4th document. So each row in this matrix is actually denoting one of these elements in the set, or one of the signalings we created before. And then it's denoting the boolean matrix, right, for the documents. It denotes what kinds of words or phrases are contained in the documents actually. Then on the left-hand side, we have several column vectors. So this vector denoting the permutation orders of the rows. So let's ignore the left 2 ones, and we can focus on this column first. This blue one first. So in this blue one, we have different numbers, right? This number is 1, 2, 3, 4, 5, 6, 7, right? They're denoting the order of the permutations. We can see for this vector, right? This vector, the 5th entry actually has 1. It denoting this one should be permutated as the first row actually, even though in the original matrix this is the 5th row, right? However, according to the permutation vector, this will be as permutated as the first row actually. So then we have this row will be permutated as a second row, right? And so forth, and third row, 4th row, 5th row, 6th row, and 7th row, right? Then when we're generating the signature for the documents according to this permutation vector, we will follow the numbers in this vector actually. So let's take a look at the first permutated row actually first. The row with number 1 here. So by checking this row, right, we can see according to this row, we will have this second document as well as the 4th document. They will contain many 1s. According to the previous page, this description. So we will define value for the document denoting the number of the first i's row, which contains C as 1, right? Because here in this example, for the second document and the 4th document, according to this permutation vector, they will have the 1s in the first permutated rows actually. Therefore, in the generated signature for this document according to this permutation vector, we will assign the values or the signature values for the second and the 4th document as value 1s because they achieve 1 in the first permutation row, right? This 1 actually is denoted by the 1 here. We can assign this 1 into these 2 entries because for this for the second and fourth document, they have value 1s in the matrix in the first row, right? And this is for these two entries, and let's look at the remaining ones, and we'll follow the order of this permutation vector. We'll go to the next entry with value 2 next. This should be permitted at the second row here, right? And according to this row, we find that the first and the third document, they will also have value 1s. So therefore, we will assign this 2 as a signature number. Actually, this order 2 will be assigned as signature number in signature result for the first and third document. Therefore, for the first and third document, these entries in signature result, we will assign this order 2 into these entries as the values. Right? You can follow me, right? So these 2 ones, because for the first permitted row of the second and the fourth document, they will have value 1s. So therefore, we can assign this value 1, this order 1 as a value into the signature matrix here for the first one. And for the first and third document, they will have the value 1 in the second permitted rows. Therefore, we will assign the second order here into the values for the signature matrix. Okay, so this is this permutation vector. Let's look at this one. This one will also have a permutation vector, right? It also have the value from 1 to 7. And we will also follow the order of these permutation vectors. We will take the first permitted rows first. So this is the first row, right? And we can look at this first row as well as the values in this row. We find the second and fourth document, they have value 1s. Therefore, according to the function description we showed before, we will assign this value 1, this order 1 as a value into the signature matrix for the second and fourth document here. Right? These 2 ones are actually the ones corresponding to the order 1 here we show here. Right? And then we can follow the order 2 here. We can look at this row instead. This row will have a value 1 for the first as well as last document. However, for the last document, we already have 1 here. We don't need to further fill in the values. So therefore, for the first document, we will fill the value 2 into its signature matrix, right? So therefore, for this signature result, we will fill in this value 2, this order value 2 into this matrix as a signature for the first document here. And we will still have 1 empty entry for the third document, right? And then we have to follow the order. We look at the row 3, this permitted row 3. We have the second and fourth row has value 1s. However, according to the previous description, we have filled in these numbers already, right? By the first row. And here we still don't have value for the third document. And then we have to go forward, go to the fourth row. Go to the fourth row, we find the first document as well as third document, they have value 1s, finally. However, for the first document, we have value already in the signature result. Then they will fill this order 4 as the value and the number for the signature of the third document here, because we encounter 1 value for the document in the fourth row. So this 4 comes from this 4. We can fill in this 4 into this entry because for the third document we have value 1 in the fourth row. And in a similar way, we can also fill in the third signature of the documents according to this permutation vector as well. We can follow these orders. We can go to the first permitted row at the beginning, and then we can go to this row. We find the first and third documents, they have the value 1, right? Therefore, we can fill this order 1 as a signature into the first document as the third document, this signature matrix. This row, right? And we can go further forward. We can go to the second row, and we have the value 1 for both the second and fourth documents. Therefore, we can fill this order 2 as a signature into the matrix for the second and the fourth documents. So in this way, we can generate the signature matrix for all the documents according to its permutation vectors. This vector will be generated randomly. So in each time, we can generate different such kinds of permutation vectors. Therefore, the signature matrix for the documents will be different if we run the algorithm differently. Alright, so this is the way we generate signature for the documents, right? And based on this signature document, we can further calculate the similarities. So according to this input matrix, we can define similar matrix according to the Jaggers coefficient as the similar scores we defined before, right? And we can calculate the similar scores between pairwise documents as shown at the bottom side. So between the document 1 and document 3, we can calculate the score between them at 0.75. Between 2 and 4, we can calculate the score at 0.75. And between 1 and 2, they are very different. The score is 0. And similar for document 3 and 4, the score is also 0. Then let's calculate a similar score based on the signature matrix as well. So between the document 1 and document 3, let's look at the signature vectors. So this is the signature for document 1 and this is signature for document 3, right? The vectors. And between them, we can find that they have 3 values, right? These 2 vectors have 3 values. However, they will only share twice with the same value, right? So for the first time, they will share the same value, and for the third time, they will also share the same value. So therefore, the probability for them to have same signatures will be about 2/3, right? 0.67. As to the probability for them for document 2 and document 4 to share the same signatures will be about what? We can retrieve the vectors for document 2 and the document 4, right? We find that they will always share the same signatures actually. Therefore, the similarity score will be about 1.0, which denoting the probability, right? As to document 1 and document 2, it will be 0 because they are all different. Similar for document 3 and document 4, right? So you can see, there still exists some gaps between the score we get based on signatures versus the Jaggers coefficient scores we calculated before. However, because here we only have 3 signatures, if we have large enough signatures, then the probability score will be approaching to the Jaggers coefficient score we calculated here. Okay, so this is how we use this MinHash function to help us define the signatures of the documents and how to use them to calculate scores, denoting similar scores between the documents.